Hello and welcome to the Microphotonics Imaging Laboratory here in Allentown, Pennsylvania. We're happy to have you with us today. Each month we're going to be going through some new tips and tricks videos to help you get the most out of your SkyScan Micro CT instrument. Let's go ahead and jump into this month's tip. Hello and welcome to the Microphotonics Tip of the Month series. Today we're going to be talking about some generic considerations you want to be thinking about whenever you're setting up a scan on your SkyScan instrument. Now there are many different SkyScan instruments out there and you might have a particular one, but today we're going to be using the SkyScan 1273 as the example. However, the intent of this tutorial is to help with the setting up of scans on any instrument. So for any specific questions you have related to how to do something on your particular SkyScan model, please refer to your SkyScan user manual for great detailed instructions. So you can see here I've already inserted a sample into my SkyScan 1273 and we're looking at a live transmission view through the image. We know it's live because we have the TV rather than the camera activated. The first step I want to do is to figure out what power and energy settings I need to use for my sample. So if I right click, I can create a transmission profile through the sample in this case, and that lets me know that I have about 4% transmission through the middle of my sample where I'm interested in imaging here. That's obviously pretty low. We would be aiming typically for 20 to 40% transmission on the low end. One key consideration to make though would be to try and find the densest portion of your sample that you want to image. So right now, this sample, instead of being a nice cylinder, has a high aspect ratio where it's really wide but thin. So we're looking through the thin portion right now and we're still only getting 4% transmission. But as we're setting this up, it would be better to try and navigate to find a rotation angle where we're looking through the long axis of where we want to be imaging, because at some point during the rotation of our scan, we're going to need to have transmission through our sample in the long direction. So now we're looking at an end-on view through the thickest portion of our sample, and we see our transmission is still about 3%, which of course is low. But by having the worst case scenario view present as we're setting up the scan, it'll help us better guide our power settings in terms of what we need to have a successful scan. So now we should work on increasing the power applied to our X-ray source as well as increasing filtering. So we use filtering, as we've talked about a number of times in other videos, to prevent beam hardening or to reduce beam hardening in our reconstructed results. And so beam hardening occurs when we have low energy X-rays trying to pass through a high density sample. Well, the low energy X-rays cannot pass through a high density sample, and so they are all attenuated at the surface of the sample. And then when we go to reconstruct the results, we see an artificial brightness at the edge of the sample, which is not real, but instead is the effect of all of these low energy X-rays striking the dense sample and not being able to pass through. To prevent that, we apply filters to our incident X-ray energy photons so that we can go ahead and just cut off all of the lower energy photons at the start before they ever reach the sample or the detector, and this helps us to reduce beam hardening. So again, refer to the instructions related to your specific model. In this case, I'm going to use the automatic filter selector window here, and I'm going to go ahead and go from no filter to a 0.5 millimeter copper filter, and you'll see the view will update as the filters are changing in position. Now, of course, some systems have manual filters. You'd need to open the door and change the filter manually, but other systems have automated filters. So here now we've only increased up to about 5%, but you'll notice that by changing the filter, the SkyScan software automatically increased my power from 70 kilovolts to 120 kilovolts. And that's going to be true for all systems, that as you increase your filtering, you need to increase your X-ray output. And this will typically be automatically done through the control software. So let's go ahead and go to our thickest filter here, a 2 millimeter copper filter on the SkyScan 1273. And that's going to be running at the full 39 watts of power. And what we see is that through the region we want to image, we still only have about 7 or 8% transmission. That's less than ideal. We would really like to have 20%, but it's not always the case that we have an optimal sample. So even though we're only at 8% here, if we go ahead and rotate the sample back to a thinner view, we'll see that in other views of the collection, we're going to have about 30% transmission. So while we would love to have 20% or 40% transmission through the whole sample, for some sample types like this one, where you have a really high aspect ratio and really dense features, that may not always be possible. And so you can still proceed with imaging in this type of cases, because in most views, we're going to have good transmission, but we do know that there will be extra noise and some artifacts that arise in our reconstructed results due to the low transmission we have when we're going through the thick view of the sample. So now that we have decided we're going to use the maximum power and maximum filtering available on this instrument, the next step is going to be to do the flat field corrections. And so the first step for doing any flat field correction is to make sure you have a completely clear field of view. That's very important, because otherwise you'll end up creating a negative image of your sample in your flat field corrections, which will make your data not usable. So on the SkyScan 1273, I can just drop the sample outside the field of view due to the large length of travel of the stage. And we see here I didn't quite make it all the way. So that's the key. You always want to make sure you have the sample completely out of your field of view and you're only looking at air transmission. For instruments where you can't drop the sample out of the field of view, you want to open up your system and take out the sample and then close the door and then complete this process. More specific instructions related to flat field correction can be found in your Bruker method notes and your user manual as well, in case you have any questions as we move along. So now that we have a clear field of view, we're going to disable our current corrections and we're going to look at the uncorrected image. And we see that we have a pretty good, smooth background image, which means that our detector is in good health. And we have an average transmission of about 62% right now, and that's kind of what we're going for. We're looking for an average of 60% transmission. If we found that the transmission was only 45% or lower, or something like that, what we would do would be go into options and we would adjust our exposure time. And again, this is going to be specific to your instrument, so you're going to need to make sure you know how to do this for your instrument. But in this case, we can go ahead and we don't need to adjust anything for this one because we're already at 60%. So if we had a low transmission here, we would increase our exposure time, which would increase our transmission. If we had too much transmission here, we would decrease our exposure time, which would decrease our transmission. So now that we have this all set, we didn't need to adjust our transmission in this case, and for most scanning, unless you're changing the power settings, you probably won't have to adjust it very often because the factory defaults are going to be there to begin with and get you pretty close. So the next step is going to go ahead and acquire our flat field references. So in this case, we're going to update flat field for our image, and then we have to decide, do we want to do dark fields or bright field references or both? So what we recommend typically is once per day you should do a dark field correction. This is going to correct the pixel readout when there are no X-rays turned on to your system, and that's going to normalize the detector with no incident signal. So you're going to set a 0 point for each pixel in your detector. And of course, that's not going to change much day to day, but we still recommend doing it once per day just to be safe. However, you should be updating your bright flat field references anytime you're setting up a new study. The only time you wouldn't need to do new bright field references would be if you're just running one type of sample over and over back to back in a day. You don't need to create a new flat field correction between each sample unless you're changing settings such as the position or the filters or the power. Those kind of settings would require you to update your flat field references again. So we're going to go ahead and do dark and bright flat fields, and we're going to let it run now. All right, our flat field corrections finished, both for our bright and dark flat fields. And in this case, the SkyScan 1273 automatically brings up my corrected images. If your instrument still keeps the images off, you can always double click on the top left corner or find the appropriate way on your specific instrument in terms of how to turn the flat fields back on. So after correcting, we see our maximum transmission is around 89% and our average is about 86%, and that's pretty good. We're aiming for about 90% transmission through our corrected flat field images. So let's go ahead and bring our sample back into position and get ready to set up the scan. All right, so we're going to be focusing on the central region here of the sample. So while we've already set the pixel size earlier based on the needs of the project and positioning our sample, we want to talk about a couple considerations. One, it's always a good idea to leave some air on the left and right side of your images when you're setting up a scan. That'll help your reconstruction stay nice and linear and help you get really good density data out of your samples if that's what you're going for. Sometimes it can be a case that someone will set up a scan where they bring the sample closer and closer to the detector in order to try and get better and better resolution. But in doing so, eventually you get to a point where you no longer have air on both sides. And so one common misconception is that even though this is truly air here on the left side of the image, we're actually going through 2 layers of plastic before getting to like the air as well. So it's not a true air reference. So that would not be considered scanning within the field of view, even though the sample is within the field of view. That's a key consideration when setting up scans. So let's go ahead and go back to our desired pixel size of 30 micrometers. And the next step is going to be to go ahead and rotate the sample through a number of different rotations. So we already know 0 look good, 30 look good. Let's do 75 degrees. And what we're looking for is just to make sure our sample is staying relatively centered and that we're not going outside the field of view on either side of our image. All right, so this looks pretty good to me. I've gone to about 180 degrees, which kind of gives me an idea of what the full 360-degree picture would look like. All right, so everything looks pretty good now. We're ready to go ahead and move on to set up our scan. So to do that, we're going to click on our Scan and Parameters menu, and that's going to bring up our scanning options. So the first thing we want to do is give the sample a clear file name and then pick the directory where we want the projection data to be stored. Next, we're going to set the rotation step. Again, this is going to be dictated both by the pixel size of your scan as well as how wide your sample is within the field of view. As your sample is smaller and smaller towards the center, you can take larger and larger steps and save time without losing data quality. However, this is a topic to be explored further, and there's a method note referenced in this month's tip article which will give you more details related to that. Next, we can decide whether we want to apply frame averaging, and if so, how much. So frame averaging is used to help reduce the noise in our final images by taking multiple images at a single rotation step and then averaging them out to kind of get rid of background fluctuation noise. So for most scans, a value of between 4 and 8 is perfectly suitable. Anything above 10 is likely not going to be giving you any benefit, and it's just going to slow down your scan. And of course, having no frame averaging will speed up your scan but will lead to more noise in your final images. Ring artifact suppression is present on many SkyScan systems, which is an option you most generally want to leave on. However, if you are worried about your sample moving or some other issues related to sample stability over time, you can save some time by turning off ring artifact suppression. with the caveat that you may have more rings that need to be corrected in your reconstruction process. Finally, the other key consideration for any system is whether or not you're going to do a full 360-degree scan or 180-degree scan. So you can see with our current settings, our 180-degree scan would be about 45 minutes. Switching to a 360-degree, we go almost double, about an hour and 20 minutes, hour and 15 minutes of time. And so why do we pick one or the other? Well, a 180-degree scan is a great way to acquire data for a fairly homogeneous sample, lower density, where we have good transmission through all views of the sample and no large disparities in density within the internal structure. For these types of samples, 180 degrees of coverage is perfectly sufficient to gain all we need in terms of structural information from the center of the sample. However, for dense, asymmetrically loaded samples like this phone, 180 degrees would lead to a lot more artifacts than if we do the full 360 degrees. We already know from setting up the scan that we have some rotation views where we have limited transmission through the sample. So in order to try and help overcome this limitation, this scan would be best suited to using the 360-degree scanning. This is also very applicable for samples where you have mixed components like metals and plastics, or really dense components next to lighter components, where you want to try and visualize both, because if you don't turn on the full 360-degree view, the dense regions of the sample may actually cause shadows or other artifacts in the lighter regions when you go through your reconstruction process. So I hope this is a quick way to get you started on some key considerations you want to be thinking about when you're setting up scans on your SkyScan instrument. As always, we thank you for tuning in to the Microphotonics Tip of the Month series, and please reach out to us here at Microphotonics with any other specific tips related to your application or instrument.
Hello. Thank you for watching this installment of our Video Tip of the Month. At Microphotonics, we strongly believe that the research you do changes the world, and we're happy to support you in your efforts through these videos, through our advanced training courses, and our annual workshops. Through these efforts, we strive to make sure that you are getting the most from your Bruker Micro CT machine. If you have any questions on this video or any other questions, feel free to give us a call or send us an email. Thank you again, and have a good day.